Hello, everyone, and welcome to this episode of Crowded Beaker and Crowded Beaker Solves. In this video, I'm going to be starting a series of videos on something called chemical kinetics. And when you hear the word chemical kinetics, you probably may be thinking of like action or motion or energy, and all of that is true. When we do chemical kinetics, we're really looking at chemical reactions and asking ourselves some questions about that reaction, such as how fast is this reaction going? You might already know that some reactions happen very quickly, and other reactions take an extremely long time to complete or even get any progress on. And we're asking ourselves the question, is there a way I can quantify that rate of reaction, how fast that reaction is actually going? And if there is, we can ask the next question, what factors are affecting how fast or slow that reaction is going? Is there anything that I can do to change the rate of a reaction, make it go faster, make it go slower? And all of that is too much to unpack in one video. So I'm planning a series of videos. And as a quick business note, I may be putting them on Crowded Beaker and Crowded Beaker Solves. Crowded Beaker for those people who have already subscribed and are continuing to watch Crowded Beaker, and for those that have found Crowded Beaker Solves as a way to help with their chemistry homework, this should appear there as well, because I'll be demonstrating some of the types of problems that you're likely to encounter as you study chemical kinetics, especially in an introductory class. Okay, so it's helpful to start looking at a reaction. This is just a reaction I chose because I liked the coefficients, and you'll be able to see where they go in a little bit. But in this particular reaction, we have dinitrogen pentaoxide, N2O5, reacting to make NO2s and an O2. And that's my balanced chemical equation. And I might want to study that reaction and come up with a reaction rate, like how fast is that reaction happening? So I want to throw on a couple of definitions just to get us started. The first, and both of them deal with reaction rate. And when we talk about reaction rate, we're actually talking about the change in concentration of a reactant or product per unit of time. And we're saying, all right, let's focus on, say, the reactant. How much is that dropping per unit of time? Because the reactants have to make products. Or how much is the product increasing over a certain length of time? And if you've gotten a long ways in math, calculus, for example, you spend a lot of time talking about two types of rates. There's an average rate, which is a rate over a period of time. So from time zero to sometime down the road, on average, how fast is this reaction going? And an instantaneous rate, which is saying, okay, at this particular moment in time, how fast is that reaction going? And so we're going to try to model both of them as we look at some data. So change in concentration of a reactant or product per unit of time. And in this unit, you're going to encounter a lot of data. You'll have some numbers to work with, some quantities to study. And I went ahead and made a sheet with some data regarding the reaction that I just showed you, the N2O5 changing over time into NO2s and O2s. And as you look at the data, lots of times you encounter data, you have to just look and see what it's telling you. Make those judgments. So I have time over here in seconds, so I can see this trial went from 0 to 2,000 seconds. And the concentration of N2O5 is given in moles per liter, and that's a pretty typical concentration. You want to make sure that it's in moles per liter. Most of the time it is, but sometimes you'll get something else different, like liters by itself or atmospheres of pressure or something. And I notice that I'm looking at these numbers, and these numbers are going down, which makes sense to me because the reactant is getting used up, and so I would expect it to go down. Now you might look at that and be like, okay, well, is this sort of happening linearly? Is it going at a constant rate? And can I even make a rate out of those numbers? And I want to demonstrate both ways to determine the rate of this reaction. Let's first look at the graph. The graph starts at 1 mole per liter, and you can see that it's moving downward. The first thing I'm noticing about this is that it's not linear. Some reactions will have a linear graph, but this one does not. It's actually slowing down and leveling out as it goes along. And we'll find out reasons for that as we go through our unit and a series of videos. So what if I wanted to say, well, how fast is it going up in this area? What is the actual rate of reaction, the change in concentration versus the change in time? So let's just say, for example, I'm going to go from, say, 0 during the first 400 seconds, okay, as it's going from 1 down to about, somewhere in there or so. But I have the data over here that I'm going to actually work with. So my average rate, and it's always good to write down what you're defining the rate as. So we're going to call it the rate is equal to the change in N2O5, so that anybody reading my work will know that I'm looking at that, over the change in time over that particular time frame. Okay? And that's my rate. So it's good to write that down and define it for anybody reading your work. And the way I'm going to do that is I want to take, for an average rate, the change in concentration. So I'm just going to actually subtract two numbers. The concentration during that time went from 1 down to 0.78. And I'm actually going to do final minus initial. That's a pretty typical thing we do in chemistry class. Final minus initial if you're taking a difference. And on the bottom, we're going to go T final minus T initial. And what that will give me, if I plug in some numbers, the molarity went from down to 0.78 from 1, and that happened between 400 seconds and the original seconds. Okay? And when I divide those numbers out, so it actually dropped 0.22 moles per liter over the 400 seconds, which works out to be 5.5 times 10 to the minus fourth, and the unit here is going to be moles per liter per second. So on average, the rate of that reaction over the first 400 seconds is 5.5 times 10 to the minus fourth moles per liter per second. All right, and you could do that for any two data points along the line there. Now, if you were ever asked to find an instantaneous rate of change, you would have to do one of two things. I'll show you the manual way here. And if you know how to do derivatives from calculus class, this is also a good chance for you to apply them. What you would do is say, all right, for example, I want to know what's the rate of change right there at some particular point that I'm at 500 seconds. That's what I picked. And the manual way to do it is to say, well, let's not take this whole range because I know that the slope is changing during that time. But you could pick a point, and the whole point of finding a derivative is to take, this is not a perfect line, by the way, is to say, what is the slope of the tangent line at that location? Okay, and I could take the change in concentration from here to here and put that in, and the change in the time from here to here and put that in, because I have a right triangle here, and it works out pretty well, and I could get a number of values similar to the one I just got for an instantaneous rate of change at that moment. All right, so hopefully you're doing well with that. I want to continue on and talk about defining it in a slightly different way. So I can define my rate of change as the rate of decreasing. And by the way, this will end up being a negative. I forgot the negative. Sorry about that. It's a negative because we did final minus initial. And the negative rate is actually okay because we can tell that it's going down. Just telling the direction of the rate change, the way the concentration is going. Sometimes you'll have a positive one, and sometimes it'll be negative, but always do final minus initial. Okay, I'm going to put up a second set of data. I made a second sheet. And the first two columns are the same as the first two columns we saw before, but the second two columns now have the concentration of NO2 and O2 over time. And since they were products, we started at 0 and moved our way upwards. That should make sense that we're producing more and more product as the reaction is going on. And those numbers came out as is, and notice they're different from what's happening here. So the question becomes, well, if these are going down, why are these numbers different from those numbers? And in fact, if I make a graph of it, which I did, you'll see that the graph looks something like this, where the blue here is the N2O5 that we saw before, And the red, you'll see a red line, a curve, and a yellow curve. And this one is for the NO2, and this one is for the O2, this yellow one. And you might be looking at there thinking, wow, that's complicated. And why is this one going up so much more than this one is coming down? And why is this one kind of sitting there at the bottom, not doing much? And the idea here is that you can define the rate any way you want it, but the rates may differ slightly in their numbers because of the fact, here's the balanced chemical equation again. The balanced equation has a 2 and a 4 and a 1. And maybe you'll agree with this. For every 2 N2O5s that are used up, there's actually 4 NO2s that are actually produced. So there should be twice as many of those as there was these that disappeared. So there's a 4-to-2 ratio or 2-to-1 ratio if you reduce it. And only one oxygen is made for every one of those. So as this thing is dropping, I'm not really making a lot of oxygen. So the amount of oxygen is only going up slightly, but I'm making a whole bunch of those, so it's going up more rapidly. Now, I'm going to show you how to solve a certain type of problem that you're probably going to see in your chemistry travels. And I'm going to do it for this reaction, and then we'll have a pause the video moment for you to try it with a different reaction. So let's say I'm studying this reaction, and I find that the rate of change, rate of disappearance of N2O5 at 0.004 is 0.004. What are the rates of appearance of NO2 and O2? All right, so the way you're going to do this is you're going to start with what you have, so 0.0040, and I'm going to say it's moles of N2O5 per liter per second. Now, the liters and seconds are not going to change, but what you're going to do is simply apply the mole ratio from the balanced equation and say for every 2 moles N2O5, which gets this unit to cancel, you're going to make 4 moles of NO2. And so your final answer there is going to be 0.0080 moles of NO2 per liter per second. Okay, you're just going to take the rate you have and apply the ratio from the reaction. Let's do it again for the oxygen. Mole N2O5 per liter per second. And in this case, only 1 mole of O2 is produced from every 2 moles of N2O5 for a rate of 0.020 moles, sorry about that, O2 per liter per second. And I will put a nice one of those around there with the heart next to it. And you can see those as my examples. Okay, so it's time for you to try. I have another one ready to roll here. We have a different reaction, sulfur reacting with oxygen to make SO3s, and we got some cool coefficients there. In the reaction above, the rate of appearance of SO3 was measured to be 0.12 moles per liter per minute this time. Just make sure to watch the time units. What are the rates of disappearance of S8 and O2 at that time? So feel free to pause the video and see if you can solve this for yourself, and we'll be back in just a second with the solution. So. Okay, well, let's check out the solution, and you can see how well you did. If you did it properly with the correct mole ratios, 1 and 8 and 12 and 8, you should get values of 0.015 moles of sulfur per liter per minute and 0.18 moles of oxygen per liter per minute. So once again, we're defining the rate as the change in some concentration versus the change in some kind of time. It can be defined based on any product or reactant as long as you're specific about it. And you can also relate them to each other by using their mole ratios. All right, in our next episode, we're going to talk about rate laws and how to determine what the equation is that governs a particular reaction. So in the meantime, happy solving, and I will see you next time.